The surprising part is that the expensive thing is not talking, it is checking. As soon as you demand reliable answers, the compute bill multiplies fast. One response becomes several passes, several tools, and sometimes a human sign-off. That is why inference is starting to look less like software and more like a factory. A factory takes in energy, equipment, and inputs, then produces an output you can measure.
Here, the output is reasoning capacity. It is metered, scheduled, and routed. It is audited, verified, and provisioned under constraints that look a lot like utilities. Power, cooling, network latency, reliability targets, and institutional accountability when something goes wrong. A useful mental shift is to stop thinking in cost per token. Tokens are a convenient unit for vendors. They are a misleading unit for operators. The better metric is verified task throughput per unit of energy, capital cost, operations labor, retry load, audit overhead, and governance friction. In other words, what did you get done and how much did it cost, once you include the real-world overhead of doing it safely? Modern inference at scale is already a production systems problem. Accelerator supply matters, but so does memory bandwidth. Interconnect topology matters because data has to move, not just compute. Batching policy matters because you trade latency against throughput. Context length matters because longer context can mean higher cost and different failure modes. Queuing discipline matters because users judge you by tail latency, not average latency. P95 and P99 delays decide whether an agent feels crisp or gets stuck in loops. Another shift is that serving and training are separating into different industrial stacks. Training is episodic, spiky, and research-driven. Serving is continuous, contractual, and operational. Interactive chat needs low latency and predictable behavior. Tool-augmented agents need robust tool calling, retries, and guardrails. Retrieval-augmented workflows need fresh indexes and tight provenance. Multimodal inference needs different hardware balance. Formal reasoning needs integration with proof tools. Batch summarization wants cheap throughput and scheduling flexibility. Cyber-physical control wants deterministic timing and clear escalation paths. Once you see those as distinct service classes, a lot of confusion clears. You stop asking, how much does AI cost us, and start asking, which workloads deserve premium capacity, and which can run on cheaper tiers. Without that, background tasks quietly compete with safety-critical tasks during demand spikes. Then the system fails in the worst possible moment, not the most expensive one. Reasoning-heavy workloads also have a specific economic trap. They are rarely single-pass generation. A serious task triggers retrieval, tool calls, policy checks, and verification passes. Some tasks add a second model review. Others require formal checks, or physics-informed constraint checks. The workflow can even escalate to a human specialist, because accountability has to land somewhere. Each step is rational on its own. Together, they can multiply compute demand by several factors, relative to a simple prompt and completion. This is where verification economics becomes a board-level topic. Every added check reduces error, but every added check adds latency, integration complexity, and cost. Leaders need a way to decide when verification is worth it, not in theory, but in the messy reality of operations. If a system influences finance, safety, employment, medical decisions, legal posture, or public administration, verification is not a nice-to-have. It is part of the product. Formal reasoning illustrates the trade clearly. Proof assistance and formal tools can raise assurance dramatically in narrow domains, like contracts, code, safety cases, and mathematical claims. Yet they introduce specialist labor and pipeline complexity. They can slow workflows, and they create new failure modes, like brittle integrations or false confidence in what was actually proven. The point is not use formal methods everywhere. The point is to budget them explicitly as their own scarce resource. Digital twins and physics-informed models push inference into an even more infrastructure-like role. A digital twin is not a dashboard you build once. If it influences operations, it becomes a continuous reasoning workload. It needs persistent state estimation, ongoing simulation, anomaly detection, and decision support. Physics-informed methods can embed constraints that improve realism and stability, especially for engineering and scientific systems. But those methods can raise model management and validation cost. So you have to fund the twin like a living system, not a capital project with a one-time software line item. Now add placement. Some inference will stay centralized because scale is efficient. Other inference will move closer to the edge because latency and connectivity are constraints, not preferences. Future network architectures, including more advanced wireless systems, make compute and communications a co-design problem. If a task is controlling equipment, vehicles, factories, or grid assets, the speed of light and network congestion become part of your reasoning budget. You can pay for low latency with regional nodes, on-prem deployments, or device inference. Or you can pay for it with degraded control quality and more frequent human intervention. Correlation is another quiet driver of both cost and risk. Demand does not spike independently by region. It can surge together, triggered by incidents, weather events, elections, market stress, regulatory deadlines, security events, or mass customer behavior. When that happens, queuing cascades, tail latency rises, agents retry, and retries create more load, which raises latency again. A system that looks fine at average load can fail spectacularly under correlated stress. So forecasting needs to treat inference fleets like other critical infrastructure, where correlated shocks are normal. Governance adds yet another layer that many teams underprice. Inference that matters must be reconstructible. After a dispute, an incident, or a regulatory review, you need to know what happened. That means provenance. Which model version ran? Which prompt chain was used? Which tools were called? Which sources were retrieved? Which policy checks fired? Whether a human approved? Governance is not just compliance theater. It is the ability to audit a decision path under institutional scrutiny. That governance burden also changes procurement strategy. If your reasoning logic is trapped inside a vendor API, you do not just have vendor lock-in, you have institutional memory lock-in. Prompts, tool schemas, retrieval artifacts, evaluations, and provenance logs become part of your operating system. They must be exportable and portable, in machine-readable forms, if you want credible bargaining power and resilient continuity planning. Operational discipline matters here as much as model quality. Model change governance is a concrete example. If an upstream provider changes behavior, downstream processes can silently break. So production inference needs version pinning, change logs, notice periods, and rollback pads. Without that, the model updated becomes a business process change, without any of the controls you would demand for a financial system or a safety system. Routing competence is the economic control lever most organizations underestimate. Someone has to decide dynamically which tasks go to frontier models, which go to smaller specialist models, which can be answered from cache, which require retrieval, which should invoke a formal system, and which must escalate to humans. Those decisions determine cost, latency, and risk. Unmanaged routing turns marginal tasks into premium calls. Managed routing turns premium models into scarce resources used only where they buy real value. The risk envelope follows directly from these mechanics. There are ordinary failures like outages, queue overload, and tool downtime. There is silent model drift, where behavior changes and no one notices until damage accumulates. There are correlated outages and capacity exhaustion, where demand and failure align. There are runaway agent loops, where retries and tool calls spiral. There are unauditable decisions, where you cannot reconstruct what the system did. There is energy price exposure, where high utilization meets volatile power costs. And there is brittle dependence on a small number of vendors, which turns market structure into an operational risk. Given all that, the most practical move is to build an inference cost ledger, now, not later. You want cost by task class, not just by invoice line. You want to know model family and version, context length, tool calls, retrieval calls, retries, verification passes, human escalations, and latency class. You also want a governance flag, stating whether the task influenced a regulated or high-stakes decision. Once that ledger exists, you can manage inference like any other production input, with service classes, verification budgets, and failover plans. Plan capacity with energy procurement too. Inference factories are energy-converting systems. Without a power strategy, you inherit cost volatility and reliability exposure by default. Cooling and grid interconnection become strategic constraints, not facilities footnotes. Over time, mature economies may treat inference capacity more like critical infrastructure, tied to grids, telecom networks, digital twins, robotics fleets, and public administration workflows. Multi-region and off-world systems cannot rely on immediate human oversight.
They need local autonomy, delegated authority, and strict audit regimes. Live reasoning, stored policy, and delayed review separate into different layers because communication delay is not a bug you can patch. Even then, reasoning remains bounded by energy, heat rejection, communication delay, institutional trust, and verification limits. So here is the line to remember. The future winners will not buy AI as an undifferentiated expense. They will run reasoning as governed infrastructure and measure it by verified outcomes.